right, so we want to talk about exponential functions and their graphs. Exponential functions will probably be one of the most practical things that we talk about all year long, and you'll see why when we get to some really cool applications of this in a few minutes. All right, so first off, when we're talking about an exponential function, we're talking about something like y equals a to the x, but there are some restrictions on a. A has got to be a number that is greater than 0 and not equal to 1. All right, so that's kind of strange. Why can A not equal 1? What if this was 1? What if it was 1 to the x? What's 1 to the 1? What's 1 to the 2? What's 1 to the 3? What's 1 to the 4? So what will we get every time? 1. So if you graph 1, 1, 1, 1, 1, 1, 1, right, that's just a horizontal line. That's a constant. So that's not an exponential function if there's a 1 right there. It's a constant function. So that's why we have to eliminate that. All right. So A has to be a number that's greater than 0 but not equal to 1. And then your exponent, x, just has to be a real number. Can't be imaginary, just a real number. So it could be positive, negative, decimal, fraction. It could even be something like pi. So here's a couple of these that we want to just throw into our calculator. So grab your calculator, doesn't matter which one. If you want either scientific or graphing, whichever you prefer. And go ahead and take a second and throw those in. I'm going to put the correct answers up here for you, so that you can make sure that you're getting those. And then I'm going to come around. If there's any of those that you're having trouble getting, then I'll look at it with you one-on-one. All right, so we said that A had to be greater than 0 and not equal to 1. So that means that A could be greater than 1, or A could be between 0 and 1. All right, so let's look at that first scenario. Let's look at y equals a to the x when a is greater than 1. So that would be something like 2 to the x. All right, y'all, we can plot anything on the face of the earth if we just plot enough points. All right, so I'm going to come over here and I'm going to make an xy chart. And, same values we normally use for x, 0, 1, 2, -1, -2, okay? So I'm going to plug those values in. All right, so what's 2 to the 1?
1 or 2, sorry.
2, so 2 to the 2. 2 squared would be 4. 2 to the 0, what's anything to the 0? 1 other than 0. And then 2 to the -1, what happens when you have a negative exponent? You flip it, right? You move it across the division bar. So that would be 1 over 2 to the positive 1, or 1/2. All right, so then 2 to the -2 would be 1 over 2 to the positive 2. So that'd be 1/4. Okay, so let's plot those points. All right, so we could go through and we could plug in 1, 2, 2, 4, 0, 1, -1, 1/2, and -2, 1/4. All right, I feel pretty comfortable with what's going on with this part of the graph as it goes off to infinity. I'm just not really sure what's going on as we're approaching 0 down here. Like, is it going to come on and come across the x-axis and come down below? Or is it leveling off there that there's an asymptote there? I just don't really know. So I need to do a little more exploration there. I'm going to put in a few more points, and I'm going to put in some pretty extreme points so I can really see what this is doing. I'm going to put in -10 and -100, all right? So if I do that, 2 to the -10, that would be 1 over 2 to the positive 10, right? Or 2 to the -100, that would be 1 over 2 to the positive 100. All right, 2 to the 10, that's a really big number, right? We don't even need to figure out what that is, but it's a big number. 2 to the 100 is a really big number. Let's think about that one for a second, all right? My numerator is staying the same, and my denominator is getting bigger and bigger and bigger and bigger. What's my overall fraction doing? Getting smaller, right? Is it switching to a negative? No. So no matter what number I put in here, that means that y value is just going to get tinier and tinier and tinier and tinier, but never go negative. So we have established then that it's just going to get closer and closer and closer to that x-axis, but never cross over it and never go negative. So there must be a horizontal asymptote there. Actually, there are two landmarks that we're going to use for graphing our exponential functions, and one of them is going to be that horizontal asymptote at 0. The other one is going to be a y-intercept at 1. Why would I always have a y-intercept at 1 for my base function? What's giving me that 1? 0. So if you had anything raised to the 0, what's that going to be? 1, with the exception of 0. 0 to the 0 is undefined, but that's not in our domain for this function. Because if you come back up here, remember that a has got to be greater than 0, so we're never going to encounter that. So that means that every single number that we would plug in a 0, we would always get a 1. So those are going to be our two landmarks. Now, of course, if you shifted or reflected or stretched or shrunk, all of that would change. We're just talking about the base function here, okay? So look at another one. This time, let's look at y is equal to 4 to the x. All right, let's start with our two landmarks. I know that there's going to be a horizontal asymptote at 0, and I know there's going to be a y-intercept at 1, and I also know the shape of this graph. I know that it's going to approach the asymptote, and I know that on the positive side of the graph, on the right-hand side of the graph, it's going to be going off to infinity. Really, the only thing I don't know is I don't know how steep it's going to be. Like, is it going to be narrow, or is it going to be a little flatter? I really just need one point over here to help me figure out how steep this is going to be. What would be an easy point to plot over here on the right-hand side? How about 1? Yes, that'd be easy to plug in, right? All right, so if I plug 1 in for x, what am I going to get? 4. So that would be the point 1, 4. And that is literally everything I need then to sketch my function. Because as we said, we knew we had the asymptote down here, so we knew the left-hand side was going to approach the asymptote. And for the right-hand side, all we needed to know is how steep to draw it. So if we have that 1 point, we know how steep to draw it. So y'all, we can graph an exponential function with 1 point if we know that information. All right, then let's look at the other scenario. This scenario was when a was greater than 1. The other scenario is when a is a number in between 0 and 1. So that would be something like 1/2 to the x or 1/4 to the x, right? Another way to write that, instead of saying 1/2 to the x, you also could write that 2 to the negative x, or 1/4 to the x, you could write that 4 to the negative x. I kind of prefer to write it that way because when you graph this variation of the function, it actually goes down. It decreases. So it's easy to remember over here, hey, when it's raised to a positive x, it increases. And over here, when it's raised to a negative x, it decreases. So I kind of like to think of it that way. Some textbooks write it that way. It doesn't really matter which way you want to think of it or how you want to refer to it. All right, so let's say that we wanted to graph 2 to the negative x. That's the same thing as 1/2 to the x. So let's use that same table of values that we were using, 1, 2, 0, -1, -2. And so if we plug those in, if I plug in 1, 1/2 to the 1 is what? 1/2. If I plug in 2, 1/2 squared is what? 1/4. If I plug in 0, 1/2 to the 0? 1. So there's that landmark again, right? If we plug in -1, you have 1/2 to the -1, or 2 to the -1. That'd be 2 to the +1. That'd be 2. And then if we plug in -2, 1/2 to the -2 just means 2 to the +2 in the numerator, right? Or 4. So here are those points, and I can connect them, and you'll notice that we have the same two landmarks. We have a y-intercept at 1, and we have a horizontal asymptote at 0. So again, I'm going to be able to graph this with just 1 point. So let's look at this second one. Let's say that they want me to graph 4 to the negative x or 1/4 to the x. I'm going to graph that with 1 point, because here's what I'm going to do. I'm going to start with my two landmarks, right? So I have a horizontal asymptote at 0, and I have a y-intercept at 1, and I know the shape of my graph. I know that it's decreasing. So I already know what this right-hand side of the graph is going to do. I know it's going to approach that asymptote. Now I just need to figure out what this left-hand side over here is going to do. And again, I would just need 1 point for that. So I'm going to plug in -1. So if I plug in -1, that'd be 1/4 to the -1. And again, remember that negative exponent just makes it move across the division bar. So that would be 4 to the +1. So if I have that 1 point, now I know how steep to make this side over here. And so I can graph that exponential function with 1 point. All right, so let's talk about domain and range for our exponential functions. Looking at this first one that we worked with over here, what was your domain? What x values did you use? All of them, yes, all real numbers. So we could give interval notation, -infinity to +infinity. All right, how about your range? Yeah, so if we start down here at the bottom and we start coming up, the very first y value that we get is we're approaching that asymptote of 0, and then we go off to +infinity. So it would be all of the values greater than 0. We're not equal to 0, right? Remember, we plugged in these really big numbers over here. We plugged in like -10 and -100, and we saw that it's never going to cross over that x-axis and be 0 or be negative, that there's an asymptote there. So our range is going to be greater than 0. So interval notation would be 0 to infinity. All right, how about the domain for the decreasing function? What's the domain of our decreasing function? Yep, same thing, -infinity to +infinity. How about your range? Is it the same as well? Yep. So domain and range are the same for all types of exponential functions. Okay, so it doesn't matter if it's increasing or decreasing, it's going to have the same two landmarks, and it's going to have the same domain and the same range. Okay, so remember that our goal has been to learn what a base function looks like, and then we can use our stretching and shrinking and shifting and reflecting to create all kinds of different graphs without having to plot points, right? Okay, so let's start with this first one up here. We've got y is equal to 3 to the x. All right, so was that the increasing function or the decreasing exponential function? Increasing, right, is the one that goes up. What are your two landmarks? 0, 1. And y equals 0 is your horizontal asymptote, okay? So I know I've got my horizontal asymptote right here. And then I know I've got my y-intercept at 1. So really all I need is 1 point to know how steep to make this. So what happens if I plug in +1? What do I get? 3. So I would have the point 1, 3, and literally that 1 point is all I need to sketch that function. So there's my base function like we were just doing a moment ago. All right, so now let's start altering it. What's this +1 going to cause right here? It is going to cause a shift, horizontal or vertical. Is it stuck to the x, or can it be moved to the other side and grouped with the y? It's stuck to the x, so that's a horizontal shift. All right, horizontal shift of what? -1, because remember it's the value subtracted from x that's the horizontal shift. So -1 is being subtracted from x. So I have a horizontal shift of -1. Okay, so just use the exact same thing you used to graph that first one. Okay, I can use my asymptote, and I'm going to take these 2 points that I used right here to graph the original and just horizontally shift a -1, horizontally shift a -1. So if I horizontally shift those 2 points, then I have everything I need to sketch my horizontally shifted one. All right, then look at the next one. Look at the red one. All right, so for the red one, what's this minus 2 going to cause right here? Vertical shift, yes, because that one can be moved to the other side and grouped with the y, right? That is a vertical shift. Vertical shift of what? -2. So vertical shift of -2 or down 2. So if you moved it to the other side, it would be y plus 2, right? So what's being subtracted from x is a -2. If you leave it on this side, you look at the number exactly as it is. So vertical shift of -2. So I'm going to take my y-intercept of 1 and go down 2. So where would it be? -1. This point, I'm just going to go down 2. I normally have an asymptote at 0, but if it goes down 2, where will it be? -2. So now I have everything that I need. Go ahead and sketch that graph. So again, we're just using the exact same 3 points that we used to graph the original, or the exact same 3 things. The 2 landmarks, the asymptote and the intercept, and then that 1 additional point. All right, look at the green one. For the green one, we have a negative out in front. What's a negative out in front of the whole function cause? Reflection, yes. So it's going to cause a reflection in what? X or Y? X, reflection in X. So a negative just in front of the function is a reflection in the x-axis. So let's go back to our original blue curve and reflect that in the x-axis. All right, and then for our last one, we actually have 2 different ways that we could think of this fuchsia one down here. So when you look at 3 to the negative x, how could you approach that? Okay, so you could think of it as 1/3 to the positive x, absolutely. So if we did it that way, if we did 3 to the negative x or 1/3 to the positive x, if you look there on the previous examples that we worked on, is that the increasing one or the decreasing one? That's the decreasing one, right? That's that second type of function, that second type of exponential that we looked at. So you could graph it as the decreasing exponential function with a y-intercept of 1 and a horizontal asymptote. There's also another way to look at this. When you put a negative just in front of x and plug it into the function, what does that cause? Instead of a negative out in front of the entire function, you put a negative just in front of x and plug it into the function.
Reflection of y-axis.
Yes, that is the reflection in the y-axis. So y'all look at this. It does not matter which way you do that, you get the exact same graph. If I take my blue function, that was the original, so this blue one, that's the original, and I reflect it in the y-axis, I'm going to get this fuchsia one right here. Or if I go back to what we talked about earlier, that if you have 3 to the negative x, that's a decreasing function with a horizontal asymptote at 0 and a y-intercept at 1, then you would just need to plot 1 point. You could plug in -1 and get +3, and that 1 point would tell you how steep to make it. So either way you go, you're going to get that exact same graph. So 2 different ways to approach the same thing. Okay? So we should be able to graph both the increasing and the decreasing function, the exponential function, and we should be able to shift it, reflect it, stretch it, shrink it, all those things that we already know how to do. We should be able to put it in combination with that. Okay, so just for review, here are the 2 functions that we were working with. Here's the decreasing one, a to the negative x, or you could think of it as 1 over a to the x. So that was when our value was between 0 and 1, right? And that had the y-intercept at 1 and the horizontal asymptote at 0, domain of all real numbers, range from 0 to infinity. And then here was the increasing one. So the increasing one was when we had a to the x, where a was a number greater than 1. And again, domain all real numbers range from 0 to infinity. So we want to look at a specific type of exponential function. It's actually called the natural exponential function. And it has a base of e. Now, e is kind of like pi. It's non-repeating, non-terminating, and so it's such a difficult number to work with. We just assigned it a symbol like we did with pi. We assigned it e, and it is the natural exponential. All right, so e is just 2.71828, and it looks like it repeats, but if it goes out a little bit further, it starts deviating. So it genuinely is irrational. But let's just round this for just a second. This 2.7, let's round that to 3, okay? If this was 3 to the x, would that be the increasing function or the decreasing function? Increasing, right. And so you'll notice that the natural exponential function is just the increasing function with the same two landmarks and the same domain and the same range. It's just a specific type of that exponential function, and we'll use it a good bit of the time. All right, so let's look at some applications of exponential functions. One of the most common uses of exponential functions I ran into this weekend when I was purchasing a vehicle, because it's all about interest, right? Finding the lowest interest rate and how long are you going to finance it? Are you going to finance it for 60 months or 72 months? And that makes a big difference in how much you end up with the total cost or the total amount, all right? So it also works when you're putting money into the bank. All right. So the equation that we have is going to be the amount is going to be the principal. P stands for principal, the amount that you're depositing or that you're paying or that you're putting in, or the amount that it costs, whatever the scenario might be. And then 1 plus R is going to stand for your rate, and we're going to write it as a decimal. N is the number of times that interest is compounded, and we'll talk about that in just a second. And then T is your time in years, okay? So one more time, P is your principal. So A, of course, is your amount of interest. P is your principal. R is your rate, written as a decimal. N is the number of times it gets compounded, and T is your time in years, okay? So that will tell me my final amount out here that includes the interest. Now, when we said N is the number of times it's compounded each year, interest can be compounded annually. That means one time a year. It can be compounded semi-annually, so that's twice a year. Quarterly, how many times a year do you think quarterly is? 4. Monthly? 12. Daily? 365. Yeah, so N is just going to be the number of times that it gets compounded. We also said we're going to have to write our rate as a decimal. All right, so if you were writing 9% as a decimal, what would you get? 0.09. Yes. Okay, so 0.09 would be that percent as a decimal. Okay. Also, just a little note here, reminder that as we said, we should know what these base functions look like and how to shift them and reflect them, and that would include that e to the x that we just talked about as well. All right, so your grandma loves you, and she gives you $12,000 to invest for college. If the interest rate is 9%, please tell me where that is so I can go put my money there as well. How much would you have after 5 years if it was compounded quarterly or if it was compounded monthly? Okay, so let's start with, what is our principal going to be? 12,000. Yes, the principal is the amount you're investing. And then 1 plus the rate. What's our rate going to be? 0.09, because we're going to write it as a decimal. And if it's quarterly, how many times is it being compounded? 4 times. So 4 is going to go in 2 different places. It's going to go here and here. And then the time in years? 5. And so we're going to throw that into our calculator. So grab your calculator, if you would, please, and throw that in. And this is the value that you should get And I'm going to come around and help you if you're not getting that number to help you figure out what is going on. All right, so if we throw it into our calculator, you can see we're going to get $18,726.11. So that's not too shabby, right? So I ended up with significantly more than what I started with that Grandma gave me. Even more than a 50% increase, right? Okay, so what if instead it was compounded monthly? What's the only thing that would change? Yeah, we'd put a 12 in the place of 4. All right, so if you put a 12 in the place of your 4, if you are working on a graphing calculator, you can just scroll back up to that equation that you just had and replace your 4 with a 12. And that might make it a little bit faster and easier. All right, you think it's going to be more or less? More. All right, because it's being compounded more often. So absolutely, yes, it does end up being a little bit more the more often that it's compounded. Now, for some reason, we get this idea that when you have a decimal and a percent together, it really bothers us. All right, you still treat it the same way. What if this had been 9.5% interest? How would you write that as a decimal? 0.095, right? You're still just going to move your decimal 2 places. So don't let that bother you if there's a decimal in your percentage that you have to deal with. Now, here's where E comes into the picture, is that you can have continuously compounding interest. All right. So your grandma gives you that same $12,000 to invest for college. Interest rate is still 9%. How much would you have after 5 years if it was compounded continuously? So continuously literally means every second of every minute of every hour of every day. So the more it's compounded, the more money you make, right? So I would think this is going to be a ton more money. Actually, it's a little bit more. It's not a ton more. But we use a totally different formula for continuously compounding interest. That formula is A equals PERT, P-E to the R-T. All right, so let's set this up and then we'll go look at it on the calculator. All right, so if it was being compounded continuously, what's your principal again? 12,000, and then we've got E to the, our rate was 9%, so how are we going to write that? 0.09, and then your time in years was what? 5. All right, so here's how you're going to put that into your calculator. So I am going to put in my 12,000. Here's where E is. There are a couple of E's on your calculator. So there's one right here above your division bar. That's just a plain E. There's also another one right over here, right above ln. That's e to the x. So like if you want to raise e to an exponent, you might prefer to use that one. Doesn't make any difference. You could use your caret key with the other one. But because they're in blue, remember that you have to hit your second button first and then hit your E button. All right. And then we had 0.09%, and it was being multiplied by 5 years. All right. So again, it is more, just maybe not as much more as we thought that it might be. All right. So the more often it is compounded, then the more money that we make. So we ended up with $18,819.75. Okay, what is this compounding thing that we're talking about? Like, you know, how many times that it gets compounded? What does that even mean? Okay, so here's what we're talking about with that. Let's say that you are 21, your first year out of college, you decide to start a 401k at your first job, okay? And maybe grandma gave you $1,000 for graduating from college, so you start your 401k with that because, you know, grandma loves you. So you start your 401k with $1,000. So the first year, if that 401k is paying 5% interest, 5% of 1,000, they're going to pay you $50. Okay. So then the second year, they're going to pay you not $50. They're going to pay you $52.50, because here's what they did. They paid you 5% on this whole amount, this whole $1,050, not just on the original amount. Y'all, they are paying you interest on top of the interest. So you can see then the next year that you make $55.13. And so it just keeps increasing. I never put another penny in this 401k. That would be a bad idea, by the way. But if I did not put another penny in this 401k and I left it in there until I was 65 years old and ready to retire, look at the difference. That $1,000 has grown to $8,557. That is huge. And you can imagine if that was a larger amount. This was not a large amount though, right? And even the interest rate was not that big. I mean, it was only 5%. You can usually do a lot better than that in investments. What is the key here to making this grow? Don't take any money out. We didn't have much money in the beginning and we didn't have a big interest rate. What's the only other variable here?
Letting it sit in there for a while.
Letting it sit in there for a while. Time is the key. You need to start a 401k as soon as you can, or a Roth IRA, or some type of a savings account as soon as possible, because the faster, the longer you have it in there, the faster that money can grow. All right. If you're thinking, yeah, but it really depends on how much you put in and the rate. Yeah, that does play a factor. But let me show you another example here. All right. Let's say that we look at 4 different investors. Every one of them is investing $50,000. They're investing $5,000 a year for 10 years. Okay. They're all investing at the exact same interest rate at 8%. The difference here is time. All right. So the first person invests right out of college. They start putting in $5,000 a year from age 25 to 35, and then they stop. They only put in $50,000. If you'll notice then, when they're ready to retire, they have $787,000. But somebody that waited and said, oh man, I got to pay off my student loans, and I got to get married, and I got to start, got to get a house, and got to get a little settled first before I start planning for retirement. Okay, so they start at 35, and if you'll notice, they end up with less than half, right? Well, yeah, but then, I got house and kids and mortgage and cars, and I got so many bills. I just need to wait till I get a little more on my feet. So I wait until I'm 45. Now look what I've got. And if I wait until I'm 55, when, maybe I've paid off that house and the kids are out of the house and I can really start kind of thinking about my own retirement, it's too late. Because if you'll notice, it's not going to grow hardly at all. So give me back my youth. Let me start as soon as I possibly can when I'm younger. Okay. So I would love for somebody to have told me this when I was 16 or 17. So I would have started a little bit sooner than I did. All right. That is the miracle of compound growth and how compound growth can help you. But there are people that are going to take advantage of that, right? And use it against you. Yes? Enter credit cards. All right. Now, please understand, some of you may have taken the Dave Ramsey course that our school offers that talks about financial planning. My husband and I have taken Dave Ramsey's Financial Peace course. We've actually taught that course. And so I'm going to, just kind of give you my take on a little bit of this as we're going through that maybe doesn't, not exactly along those same lines. But here's the idea. It's your senior year and you decide, man, I want to buy some nice gifts for my family for Christmas this year. I got a part-time job maybe, or I'm starting to get all these credit card offers in the mail, and Now that I'm 18, they're starting to send me offers. I'm going to take one of them and I'm going to go out and get some really nice Christmas gifts. So, but I'm not going to put anything else on it ever again. I'm just going to spend that $1,000. All right. So you put $1,000 on at Christmas shopping, and here's what happens. Most of those credit cards run an interest rate of about 23%. So they're going to take that 23% and they're going to compound it monthly. So they'll take the 23% and they'll divide it by 12 and they'll go through and they'll compound monthly like we were talking about, okay? So for the first month, you're going to pay $19.17. But the next month you pay more. Why is that? Interest on the interest, right? Just like it could help you, it can hurt you. They're not charging interest on $1,000. Now they're charging interest on $1,019.17, right? And so you can see that next month is even higher. By the time you get out here to November, that $19.17 is now up to $23.62. By the time you get to December, you now owe $255 more than what you started with, and you never put another penny on there. That is how compound interest can hurt you, and that's what we have to be careful with. So you go to college and you have a credit card because you got these offers in the mail. So you started turning 18, you got one of them, and you said, I'm going to be so responsible with this. Like, I'm not going to put a bunch of junk on there. I'm going to put my books on there that for each semester, and my expenses, like, people would appreciate it if I bought toothpaste and deodorant. And I might even throw some ramen in there because I'm a starving college student, right? So, I mean, I might every once in a blue moon run through Taco Bell at 2 a.m. when I'm studying late. But for the most part, I'm being really, really frugal here, right? Okay, so I put $1,000 per semester on. I don't even know if you could do that stuff for $1,000. That'd be a stretch, wouldn't it? So we're being very conservative here. $1,000 a semester, and we're hoping to get out in 4 years. So we're hoping it's only 8 semesters. So I have $8,000. Okay, so $8,000 at 23% interest, and I'm just going to make the minimum payments because I don't have a ton of money. So minimum is either going to be 3% of what you owe or $25, whichever is higher. Okay, how long do you think it's going to take me to pay this off? Paying the minimum amount, not putting anything else on it, paying the minimum amount.
25.
Ideas?
30 years.
22 years. Y'all, I'm going to be in my mid-40s by the time I finish paying off my college textbooks. And these aren't even my student loans, right? And look at this. I am going to pay $13,000 in interest. That's not including the $8,000. I'm going to pay back $21,000. That is how credit cards can kill you. All right. I have people that I know that graduated from college and immediately had to move back in with mom and dad and live in the basement because they didn't have any way of paying their bills because they had such high student loans and credit card debt and everything else. That's exactly what you want to do when you graduate, right? So, am I saying that credit cards are evil and of the devil and you should never have one? I am saying that you have to be responsible, okay? So again, my own personal take here is I do have a credit card in my wallet. I have a Discover card in my wallet. And so Discover will pay me 1% cash back on everything I spend. And they will pay me 5% cash back on certain things. So like 1 month it might be groceries, and 1 month it might be gas, and 1 month it might be Walmart, and 1 month it might be Amazon, and whatever. And so last year, Discover paid me $800 for carrying their card in my wallet because everything that I automatically have to pay, my cell phone bill, my car insurance, anything that I have to already pay, I put on that Discover card because then I'll get interest on it. I'll get money back on it. Okay. So, but I had to make a rule for myself. And that was the very first month that I can't pay that card in full. I have to cut it up and get rid of it. Because as long as if I charge $1,000 and I pay it in full that month, they don't charge me any interest. I only get interest if I don't pay it off. So if I charge more than I can pay, then I got to get rid of that card because I can't handle it responsibly. But if I can handle it responsibly and they can pay me $800 a month for carrying it in my wallet, I like that. Now, there is definitely something to be said. When I go into the grocery store with a $20 bill in my hand, then there's only a certain amount of things I can buy. If I go into the grocery store with my credit card, I have a tendency to throw extra things in my buggy. And so I have a tendency to spend more when I'm just running that little plastic through than when I'm paying cold hard cash. So that's definitely something to consider as well. Okay? All right, last thing we want to talk about is something called HalfLife. Have you ever tried to give blood and they told you that you couldn't give blood because you took some kind of medicine or you had gone out of the country? Or have you ever wondered why you take Tylenol every 4 hours, but you take ibuprofen every 6 to 8 hours? Like, how do they figure out how often you're supposed to take it? When you get a prescription, how come some of those are every 12 hours? How come you can put some things in a landfill but not other things? Like, why will they not accept, radioactive, we understand, but, why will they not accept some things and they will accept other things? All of that is based on half-life. Half-life is how long it takes for something to cut in half. Okay, so let's talk about Tylenol. All right, let's just use some nice even numbers to work with. These are not accurate, but let's say that you took 1,000 milligrams of Tylenol and it had a half-life of 30 minutes. Then that means that after 30 minutes, now you've got 500 milligrams in your system. And then after another 30 minutes, you've got 250. And after another 30 minutes, you've got 125, right? And then 62.5, and then 31. And so we could keep right on going. And that's how they determine, hey, there's not much left in your system. Now it's time to take another dose, okay? So that's also why you go to give blood and they say, have you taken penicillin anytime recently? Because there's still a residual of that antibiotic in your system. And if that blood was given to somebody who had an allergy to penicillin, we would have issues, right? Or you go out of the country, you go on a missions trip for Jesus, and they won't let you give blood. You're trying to do something nice and you can't do it because you did something nice, right? Well, that's because you were exposed to things in that country that you could be bringing back in that could be in your blood that could harm that person. So let's say that we're talking about something that's going to go into a landfill, okay? So let's say the half-life of a certain hazardous material is 25 years. If originally there are 10 ounces of the material, how much is going to be left after 80 years so that they can decide whether they were going to let me put it in the landfill or not, okay? So to begin with, what's my original amount? 10 ounces, And then T, my time, is going to be the number of years, like the 80 years. H is the half-life time. That's how long it takes to cut in half. So for us, our time is 80 and our half-life time is 25 years. All right? So basically, there is still going to be more than an ounce of that left after 80 years, right? So again, that has to do with all kinds of environmental applications as well. So again, you can see how this content is so relevant to all of the different things that we've talked about today. All right.